You're listening to Let's Talk Creation with Todd Wood and Paul Garner, the creation show where we learn, grow, and worship.
Well, welcome back, everybody, to another episode of Let's Talk Creation with Paul Garner and Todd Wood. I'm Paul Garner.
And I'm Todd Wood.
It's great to have you with us. If you're a new viewer, listener, or if you're one of the regulars, it's always great to have everybody here and tuning in. And if you haven't already subscribed, make sure to hit that subscribe button, hit the notification bell, and you'll hear all about the new content that we've got coming. And we've got some great things coming up, so you don't want to miss that. Share us with your friends. Tell your friends about the podcast. Share our episodes. All of that really helps. All of that engagement to keep us finding sort of new viewers and listeners, bringing in more of an audience, and that's a great help. So, anyway, good to have you all here. Now, Todd, today you have a bit of a sore throat. I understand you're not on tip-top condition.
Yeah, a little bit of something in there. I don't know what's going on. So
yeah,
I'll do my best. I'll give it the best I can.
Yeah, you don't sound too bad. So
Thank you.
yeah, it's okay. We've got a very interesting topic. It's one that we've kind of touched on, I think, in past episodes, very briefly. We've sort of mentioned it, but we've never devoted a whole episode to it
Right.
until now. And it's one that I'm very interested in. It's catastrophic plate tectonics. So catastrophic plate tectonics is the model for understanding the global flood that some of our viewers and listeners will be familiar with, others perhaps less so. And we wanted to sort of introduce it and begin to sort of dig into what CPT, catastrophic plate tectonics, is, what it's all about, why it's important, and so on. And to help us sort of talk through all of this, we've got a special guest, Dr. Sarah Peterson. Sarah, welcome to the podcast. It's great to have you here.
Thanks for having me.
Now, Sarah, this is Sarah's topic because Sarah did her BS and MS in geology at Arizona State University before then completing a PhD in geophysics at Northern Arizona. And she is an online faculty member with Liberty University. And since she got her PhD in 2021, she has been working on geophysics with Dr. John Baumgardner, who is a very significant figure in this whole story of catastrophic plate tectonics, as we will find out. So Sarah has a fantastic sort of background to be able to talk to us about all of this. So welcome, Sarah. It's really good to have you here, and I'm looking forward to this conversation very much.
Me too.
I guess we should begin at the beginning with plate tectonics itself. And I guess a lot of our viewers and listeners will be familiar with that term. But what is plate tectonics? Just fill us in on that to begin with.
Plate tectonics is just the theory that the Earth is broken into different tectonic plates, and they've all been moving around and shifting and bumping into each other.
Okay, so
Okay.
simple as that. So we should probably think, I suppose, about Earth structure as well, because plate tectonics, you're talking there about these sort of tectonic plates moving around, sort of colliding and so on. That's just the kind of outer shell of the Earth. So sort of fill us in a bit on Earth structure and how that relates to what's going on at the surface.
Yeah, so we have the Earth is broken into the upper part, the crust, and or called the lithosphere, which is both the crust and the mantle. And then underneath that is the asthenosphere. So basically, the lithosphere is moving around on top of the asthenosphere, which isn't exactly liquid, but it's plastic in nature. So the plates can shift around it in that way on top
Yeah.
of it. And then, unrelated to going all the way down to the core. I didn't do the third the third layer. It's lithosphere, asthenosphere, and then the Earth's core.
Yeah. And as geologists, obviously what we're studying is mostly sort of surface stuff. And I don't think we've directly sampled deeper than about the top 3% of the whole of the Earth. So, the Earth is, we think about all the processes at the surface, but there's a lot going on under the surface. So there's the core, um, which is sort of metallic, iron and nickel, and it's got sort of a solid inner part and a liquid sort of outer portion. And then you've got this thick rocky mantle that you mentioned, um, which, although it's solid, it kind of deforms in a plastic fashion because it's under such incredible sort of extremes of temperature and pressure. And
Mhm.
then you've got this sort of scum on the surface, the crust. And yeah, so those tectonic plates, they're actually crust plus a bit of the upper mantle. So
Right.
that's the lithosphere, and that's what's kind of moving about these lithospheric plates. So how was this theory developed? Because there were some precursors, right, to sort of plate tectonics.
There's
People had sort of speculated about the continents splitting apart, but plate tectonics is actually quite a recent scientific model.
I think a lot of people don't know that because there's just such, especially in just the general mainstream science world, it's like the younger generation doesn't even realize it wasn't until the 1960s, 70s that plate tectonics even was really a thing. In fact, if you were for plate tectonics around that time, you could get in trouble with universities. You could lose tenure as the professor. People thought it was a ridiculous theory because there wasn't enough information. But Alfred Wegener is the one who came up with it, forever ago, the idea of continental drift, that all the continents are, drifting around, but he couldn't explain how because we didn't understand the structure of the earth and how the plates move. So he was just noticing that all the continents look like they fit together and have moved apart and they geologically align where, rock humits on like the coast of the eastern coast of South America and North America lines up with geologic units in Africa and Europe, and you can understand like, oh, they look and it makes sense that they were together and pulled apart, but everyone thought he was, ridiculous. And I always thought that this is a really important thing to teach my creation science students that I have to understand that, geology is constantly changing if they're telling you that, today we know everything, everything is great. 50 years ago, 60 years ago, plate tectonics was not accepted. And now we have all this new evidence that shows that it's true, including, we didn't talk about this, but seismology and geophysics has really opened the doors because we can't dig down deep enough to look at the mantle and see what's happening. But when we set up seismometers, whenever there's a large earthquake, it sends out waves and you can read the interior of the earth kind of like an ultrasound, and then you can create images of the earth to kind of see what's going on there.
Yeah.
Yeah, but sort of uh, I guess, how it's changed over time and sort of all these ideas and some evidences, and then it wasn't really accepted, I would say, until seismology and other things have sort of showed without a doubt that plate tectonics is occurring.
Hmm.
So
Yeah.
can I
So,
jump in here?
go ahead, Todd. Yeah.
So what I learn about tectonics as a lowly biochemist as I am, um, so I always see, these maps, right? And they have like earthquakes plotted on them, and you can see they just line right up with these what are purported to be the boundaries of the plates. Now, when were those maps developed? Was that something that Wegener would have known about? Did they know about what earthquakes were and how they occurred in places? I mean, I assume they knew certain places were prone, but I don't know that they had maps of it all.
No, I don't think they had maps of it all because also we didn't have seismometers,
Ah,
everywhere. Well, and that's really, I mean, you could map all the active volcanoes maybe, but
okay.
seismology is more recent, and in order for seismology to have a global map, you need to have global seismometers. And the more seismometers you have, the more detailed picture you can have of what's going on in the earth.
Ah,
That's
okay.
only have it, in the last 50 years, and I would say since the '90s, there's an initiative to be like, "We need to get more seismometers out there." And, between my master's degree and my PhD, I actually worked for something called the EarthScope National Office, and they were an NSF initiative, in North America to deploy seismometers across the United States and into Alaska over a period of about 8 to 10 years and collect, more high. It's sort of like having more pixels on a photo, have
Hmm.
high density seismometers, move them along, collect so that each seismometer is in place for 2 years so we can get a more detailed map of the North American interior. So all that stuff has happened in the 2000s to recent. So only in the last 20 years have we started having really detailed maps of that sort of thing.
Mm. Yeah, I mean, people noticed, didn't they, that kind of jigsaw fit of the continents, and they'd noticed that for a very long time. 16th century map makers were kind of noticing that it was a bit like a jigsaw puzzle if you kind of closed up the Atlantic Ocean basin, but they didn't really have a good explanation for why that were the case. So some people, I think, were sort of speculating, well, maybe the Atlantic Ocean basin was a big valley that had been carved out by erosion and things like this. But it wasn't really until I guess sort of Wegener came along that he kind of proposed this idea of drift, that the continents had actually split apart and moved apart. And but yeah, there was a lot of data that he was still missing, as you say, because uh, I I guess that crucial period was the sort of period from the war, the Second World War, through to sort of the 70s. And actually, a lot of the mapping of the ocean basins was because of submarine warfare during World War II. So, they were interested in magnetics because that helped in submarine detection, and they were interested in the physiography of the ocean floor. And all of those insights just sort of came together, didn't they, as sort of clues that added up eventually into this sort of concept of plate tectonics.
Mm, that's
Uh, Perhaps you could just tell us about some of those sort of insights that came, particularly in the 60s, where people were studying sort of seafloor magnetism and things like that. What were the big clues that sort of pointed people to plate tectonics?
One was, magnetic pole shifting that you can see whenever new, so at, what's called divergent plate boundaries, the plates are pulling apart, and, in the places where it's pulling apart, magma from underneath is rising up and creating new seafloor. And when it comes up, as the magma is cooling, the magnetic alignment of the grains in magnetic minerals aligns to where the North Pole is. And you can see on the seafloor with sampling it that this magnetic signature changes over time, showing that as new seafloor is created over time, it has moved and has created these stripes. And, it's showing that there's this movement or a change in orientation of the plates, etc. So that was a huge early one before we had full seismometer maps. Um, and I'm trying to think what else that we haven't mentioned. There's also geodetic data. I'm not exactly sure when that was the case, but since we've had GPS, enough satellites to accurately position stuff, we can literally show that the plates are moving slowly over time.
Yeah.
Big GPS is accurate. So that, I mean, that's since satellites, that's probably more, 70s military and
Yeah.
technology, Cold War technology. Now we could see like, wow, these sections, especially close to plate boundaries, are moving faster than interior continents, showing that these plate boundaries are active.
Yeah.
So when you say
Yeah.
moving faster, how fast are we talking here?
We're talking the rate that fingernails grow now.
Oh,
So
wow.
2 2 to 3 centimeters a year, sometimes 5. Really fast ones like the India plate are going like 7 or 8 centimeters a year or something.
Centimeters a year. Wow.
And so
Yeah.
it's low. It's low now.
Yeah.
Right, right.
Yeah. Yeah, and that obviously raises a potential issue because, as we've said, plate tectonics is a really successful theory. It's been the kind of unifying theory in the discipline of geology, helping us to sort of understand how the world works. And it explains this enormous range of data, magnetic data and the structure of the sea floor and distribution of earthquakes and volcanoes and mountain belts. All of this stuff is kind of explained well by plate tectonics. But we've got this big problem, which is that when we measure the rates of plate movement today, it's really low. So I mean, you take something like the Atlantic Ocean basin. and it's going to take 100 million years or something to open up. So that's a problem for creationism, right? So perhaps you could sort of begin to help us understand how creationists have set about solving that problem. What kind of insights came from experimental work, particularly into sort of mantle minerals?
Um, Mantle minerals, or maybe that's
Yeah, so because there were some experiments, but I think in the maybe 60s, 70s, looking at deformation of mantle minerals that sort of, yeah. So it was kind of a clue that got John Baumgardner, I think, sort of working on this whole problem.
right, right. I can't speak 100% to that because that's not exactly my expertise. But I mean,
Sure.
even I saw it in grad school. You can
Yeah.
see at the surface, at this, field geology, you can see minerals that have been created at the surface that imply that temperatures and pressures were super, super high at these rocks that were near the plate boundaries. And that doesn't make sense with the current rates today. There's no way you could get the temperatures and pressures that we're seeing in these rocks. So it implies that the plates had moved faster in the past and there's something catastrophic that occurred, which is something, regular uniformitarian geologists will just trying to ignore it and be like, well, it was just longer periods of time, but that doesn't make sense with, the rocks we're seeing. You're seeing mineral assemblages that should not be together at all, and they
Right.
can't explain them because when they plot out charts of what minerals should form at these stable temperatures and pressures, you're seeing minerals together that should not be together. And it's a huge metamorphic petrology issue right now. This big problem of kind of what disequilibria is what the term is, where, it's clear that something so fast, so catastrophic must have been happening that when these minerals were forming, they were not in equilibrium. So that's one line of evidence that sort of, I think when uniformitarian geologists started accepting that maybe plate tectonics was real, it was such a huge opportunity for creation geologists to go in and be like, aha, this is the exact evidence that shows that something catastrophic in the past has occurred.
Mm.
And instead, uniformitarian geologists were like, we're looking at this, it doesn't make sense. They tried to ignore it for a long time until they couldn't anymore. And then now they're trying to fit it into the theory they have of millions of years, slow rates, but they keep getting all these lines of evidence from several different geology fields. And I just gave one from metamorphic petrology that just does not make sense with slow rates. You
Mhm.
have to be willing to say maybe the present isn't the key to the past, which is the principle on which all uniformitarian geology kind of rests on. What we see today, all the rates, everything today is the same as what happened in the past. But it can't be, because if everything were exactly the same today, how'd we get these rocks that cannot form today? How do we, oh, well, why are we observing these things? Mountain building, even. There isn't
Mm.
active mountain building going on with the rate of plate tectonics that we have today. It
Mhm.
can't be explained, by uniformitarian geologists, so that's the tectonic problem of how do we explain the mountains even with plate tectonics, because that's not really, something that's actively ongoing to generate mountains today.
Yeah. I mean, the whole concept that the continents are not in the positions where they were originally, that they've moved around, that whole ocean basins have opened up, and that strikes me immediately as something that is a big challenge to sort of uniformitarianism, in at least in its in the way it was originally conceived.
And that's
These kinds of changes are so dramatic.
Yeah, on that note, the age of the seafloor is a huge problem because, if plate tectonics has been going on for, they don't even know, no, uniformitarian geologists don't know where to put when plate tectonics start because they can't figure out how it could have even started, what would have happened to break up the Earth's plates, and so they just don't really think about it. They're like, "Ah, it happened way back, probably, 4 billion years ago or maybe even longer ago that this occurred." But the ocean floor, what we have remaining, what is still on the surface, is only in the last 100 million years, and if you look at, and even less than that, is it very, very young seafloor that we're observing. And so that means that the entire ocean basin has formed recently. And how it must have been going faster because using their rates, you can't get that in 100 million years as they
Mhm.
have. I think it's even younger than that, maybe more like the oldest seafloor we have is more like 60 to 80 million years ago, which means the whole thing has opened up like since the Cambrian. And then so that doesn't make sense to anybody. How did that happen so quickly?
Yeah. And you say quickly here. To put this into
Yeah.
perspective, right? So the Earth is assumed to be 4.5 billion years, right? So that's 4,500 million years.
Exactly.
And if you're saying the ocean floor is less than 100 million years, that's one part out of 45. So that's like 2% of the age of the supposed age of the Earth. So that is startlingly young, a
Yes.
startlingly young surface. Uh,
Yes.
and that suggests that the plates have just been. I'm not sure how to wrap my brain around that. I mean, the entire ocean floor would have to be undergoing complete replacement every 100 million years or so. That's impressive.
It
Yeah.
is massive, and it's not explainable by uniformitarian geology. They cannot explain it, especially not with saying the rates today are have always been the same. It can't be the
Mhm,
case.
mhm. Now, you've been doing work with Dr. John Baumgardner, who was one of the creationist pioneers, sort of working in this whole field of developing catastrophic plate tectonics.
Mm.
I mean, what can you tell us about the work that he did and how he kind of originally got into this field and some of the sort of pioneering research that he carried out?
Yes, he was an engineer and not a geologist at the time when he started hearing about plate tectonics, but he was involved with the creation community. And, when he heard about plate tectonics, he was like, "This just has to be what happened during the flood. It just makes so much sense, but somebody needs to be willing to do research on this." And, he talked with a few creation people and decided that it was time to go back to school and get his PhD in geophysics, which he did, I think, in the, '70s, late '70s to early '80s. And, all with the motivation to use what he learned to figure out how plate tectonics could fit into the flood, and with the idea that plate tectonics was occurring during the flood very, very quickly. And it's developed over time to sort of be a realization that plate tectonics probably occurred during creation week. And we had like all things moving around, but then we're at in the flood, the supercontinent that was, existing, it was one continent, that one broke apart again, moves around a couple times, and then comes back together towards the end of the flood. A lot of movement during the flood.
Mhm. And he developed a kind of supercomputer model that allowed him to sort of model this rapid tectonics and particularly what was going on in the interior of the Earth in the mantle.
Yes.
Just tell us a bit about that, the sort of modeling that he was able to do.
Yeah, Terra is a Fortran-based, computer program that allows, you to mathematically set a model of the Earth and, move things around in both 2D and then now in 3D as a 3D version as well, where he can put in all the geophysics parameters into his model, the density of the mantle materials, all sorts of things that he can put in, making sure that it's, following the laws of physics for movement, and then showing that, by something called it's a runaway subduction. Once, you start subduction going, the density of that crust pulls down really, really
Mhm.
quickly, and you suddenly have these subducting plates into the mantle, which causes everything to speed up and move really, really fast. And so that idea was sort of the breakthrough, with his modeling of being like, "Well, this can occur once it breaks and starts going, it speeds up really, really fast as it's moving into the mantle." Uh,
Yeah, yeah.
and
S
it's physics-wise possible.
Just to kind of clarify for our viewers there. So you were talking earlier about hot material coming up at sort of mid-ocean ridges where plates are diverging, where they're spreading apart. But to compensate for that, those ocean plates are also being destroyed. They're descending back into the mantle as they cool and they kind of get denser because they're colder, so they have a tendency to sink.
Yeah.
And along these things called subduction zones,
Right. Those are
they're kind of
convergent.
descending back into the mantle. Yeah.
Right. Correct. So, yeah, I guess I didn't explain, but there are 3 types of boundaries. The divergent, where they're moving apart, and that's usually in the middle of the ocean because it's creating dense material, so it's lower down and water covers it. And then at subduction zone regions, that's where you have 2 plates, converging, which can be 2 oceanic plates converging under the ocean, we have that. Then also as an oceanic plate hits a continent, a continental plate, it's the oceanic plate kinda always loses that battle because it's more dense, so it seeks sinks under, the continent there, and that's a convergent boundary, and then the 3rd
Mhm.
type of boundary is transform, where things are sliding past each other. Um, that's like the San Andreas Fault. They actually generate less earthquakes, less tsunamis, less chaos to have a transform boundary because 'cause they're just 2 plates sliding past each other.
Mhm.
Convergent boundaries generate a lot of chaos, a lot of,
Yeah.
all the big earthquakes, all the big tsunamis we have, they occur at plate boundaries that are convergent and, in
Uh-huh.
production zones.
Yeah. So you mentioned there this idea of sort of thermal runaway. So this plate, this ocean plate during the flood is dipping down into the mantle. It's kind of sinking into the mantle, and it triggers this process of thermal runaway. Um, just explain for us a bit about how that works, how that process, that runaway situation develops.
Um, how it starts, we're
Yeah.
in the beginning, that's a good question.
Yeah.
Nobody knows what
Okay.
exactly started it initially. But what we do know is once it gets started, it gets going really, really fast. So I don't know what, conventional geology and creation geology, they do not know what initiated like the breaking of the plates and how this started. But to a creation geologist, we can be like, well, I'm sure God did something to at the beginning of the flood that was catastrophic that caused it. I mean, it talks about the fountains of the great deep being opened up. Now, some people think of that as just, water shooting out, but it's also something we observe at mid-ocean ridges. If you are pulling apart the plates really fast and you have hot upwelling, magma, it starts heating up, the ocean water as well and causes water to superheat, which creates steam vents at the mid-ocean ridges. And so that already you're creating this material, it's kind of forcefully coming out and then it's pushing, it's called ridge push, as it's generating all this new magma material. If it, originated at the mid-ocean ridge, it's all this magma material is piling up and there's sort of a density thing happening with the plate where it's piling up, it's dense, and it wants to push out from the center and push those plates down at the subduction zone regions.
Yeah.
If it happened where it initiated at a subduction zone region, which I don't know, it makes the Mid-Atlantic Ridge thing kind of makes more sense to me from a physics standpoint, but it could have also happened maybe at a convergent boundary, and then just as it broke there, the density of the plate right against the, where it's broken, if it starts to subduct a little bit, once it gets going, the density pulls it down. But I think
Yeah.
ridge push, and I think Dr. Baumgardner as well would be, more into this idea, which is, contrary to conventional geology, thinks that it's always a, slab pull. So the main driving force is at the subduction zone where the plate is being pulled down. But if things are happening really fast at the mid-ocean ridge, the divergent boundary in the middle of the ocean, that's ridge push, and the density
Yeah.
up of the material is actually pushing the plates out to
Yeah.
to generate it.
Yeah. And so as this plate descends, it's basically heating the mantle, sort of warming the mantle around it as it's sort of deforming it, and that this is what is causing this sort of thermal runaway. Um,
But I wouldn't say
is
that
that right?
the slab isn't heating up the mantle necessarily. It's colder and denser, so it kind of be the opposite. It's cold and dense, so it's sinking down
Yeah.
into and then warming up. The slab would be warming up as it goes down into the hot mantle.
But there's kind of frictional heating presumably around the slab as it descends through the mantle.
Frictional heating only would happen in like the brittle ductile zone, which is
Mhm.
close to the surface. Um, I'm not sure how much frictional heating is going on once you get out of the brittle fracture sort of zone anymore. You get into plastic material, plastic behavior. Although, if the plate's sinking fast enough, it wouldn't heat up quite to that level quite yet, but it's less frictional heating, I think, and more. I mean, there is some shear heating along the fault, which should be accounted for, but I think most of it is convective. That's ongoing.
Yeah. And one of the effects, as I understand it, as all of these processes are going on, they're all connected. So you're having the production of the hot rock at the mid-ocean ridges. You're having the older seafloor subducting and along these sort of convergent zones. But because you're having this hot material um, kind of produced at the mid-ocean ridges, that material is sort of thermally expanded. It's buoyant, so it causes the level of the sea floor to rise. And I think I saw in the simulations, this has an effect on sea level.
Yes.
So this is basically how the continents got flooded, we think. Is that right?
Yes, that is a big part of it. That and anytime you do have a large earthquake from these very large faults moving as well, which probably would happen. The plates aren't perfectly smooth, so they might have some seamounts, islands, and things they're trying to subduct. Well, it's going to be hard to subduct that, so it probably will get stuck for a second, and then once it breaks and resumes, those are massive earthquakes that are happening along the coast, and then those can generate tsunamis. And Dr. Baumgardner has actually spent quite a bit of time with a separate group of people that are doing research with him, trying to simulate these mega tsunamis and correlating them with mega sequences in geologic units where we see massive sea level rise and all these units deposited and then sea level drop. It goes back down and then massive sea level rise. And there's, I think, six mega sequences that occur
Mm.
like this throughout the geologic record.
Yeah. So we get these kind of pulses of tectonics and flooding of the continents. I mean, I can imagine, well, I can't imagine the earthquakes that would be produced by trying to subduct a seamount. Yeah, a
So
big underwater sort of mountain, trying to subduct that at rates of meters per second. I mean, it's mind-boggling.
and that's something I think we didn't mention. We are talking meters per second of plate movement, not centimeters per year, which is what the current rates are. Meters per second, which is huge. I mean, the entire Earth is completely changed from this.
Yeah. 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 So we have this really dramatic sort of dynamic picture of the flood. Um, Very different from this kind of children's storybook image of the flood where the rain comes down and the waters rise and then it recedes and it leaves a world that looks pretty much similar to how it did before, how it was before. I mean, what you're describing is very different from that, right?
Yeah, oh yeah, and what we're talking about is the entire geologic record pretty much of sedimentary rocks. So every unit that you see in the Grand Canyon, pretty much like all of that was laid down during the flood in over a span of a year. That's the other thing people forget. It talks about 40 days and 40 nights that it rained until the ark is lifted up, and people think, "Oh, the flood was only 40 days." No, if you keep reading in Genesis, it explains it's ongoing for months, for a full year that this is ongoing of just absolute chaos, rapid
Yeah.
plate tectonic, and that much sediment being deposited, moved around, changed. I mean, it's a totally different Earth once Noah sets back down with the ark on Ararat
Right.
Mountain region.
Yeah. 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 Um, this is really
Mind-boggling,
interesting.
really. I
It
mean,
is
I'm
mind-boggling.
struggling to think. So meters per second, you're talking about, you're getting into, how fast we run, um,
Yes.
not just how fast our fingernails grow, our hair grows.
Mhm.
It's very, very different orders of magnitude, different speed, which creates, as you say, this massive momentum. And I imagine if you're trying to subduct something that fast and it hits a seamount, that alone would be a big shock wave. And then to break it off and to keep subducting, that creates another massive shock wave. It's hard to wrap my head around because
Yeah.
it's so massive.
Yes.
Yeah. Yeah. It's really interesting. I was reading recently about a Triassic rock unit in Britain, here in Britain, where there is a seismite layer. Now, a seismite is where you have sediments that have been disturbed by earthquake activity,
Hmm.
and it kind of messes all the bedding up, in the layer. And the biggest earthquakes that we have experienced in historical times produce seismites, but they're kind of a few centimeters in thickness. This seismite in Britain is between 2 and 4 meters thick,
Yep.
and they have no idea, apart from a kind of meteorite impact, what could possibly have produced that seismite. But there isn't really any good evidence of a meteorite impact. So what do they do with that? Well, I immediately think of catastrophic plate tectonics. um, because, I could imagine that, that's going to produce the kind of seismic shocks you need.
You have no idea how many times, my students, they'll read these articles as part of their assignment where it's secular, or sort of uniformitarian based articles. And it's always like scientists are baffled by this new and as you're reading it, you're just like, catastrophic plate tectonics explains that. Immediately when
Mhm,
when I'm reading these articles, it's like they are baffled. They cannot understand
mhm,
how we're observing this. How could this happen? And then they come up with all these strange reaching for it ideas, like meteorites or something to try and explain it. And it's like, or maybe, there was one catastrophic big flood that allowed you to form these features that you can't explain right now.
mhm. And that kind of brings me on to the other thing we wanted to talk about, which is we said earlier, plate tectonics has been a really successful theory. It sort of explains so much. All of these different observations about continents kind of fitting together, the coastlines of continents, and the magnetic stripes on the sea floor, and volcanoes and earthquakes. But catastrophic plate tectonics actually helps us to explain some things which conventional plate tectonics, doesn't really explain very well.
Yes.
And I know that you've uh, done some work, particularly looking at the tectonics of Western North America and trying to sort of show how catastrophic plate tectonics can shed some light on what are otherwise quite puzzling features of the geology of that area. So, could you tell us a bit about that?
Yes. So Western North America, the Rocky Mountains, Grand Canyon, everything over there is probably the most well studied, well looked at region for geologists in the world, I would say, because, it's mostly in deserts, a lot of exposed rock. It's not a politically unstable regime, so people have access to it. And yet all uniformitarian geologists are completely confused as to how did the Rocky Mountains form? How did the Grand Canyon form? How did the Colorado Plateau uplift as high as it did? What about the Great Plains, which they never want to talk about? There's just so many features that we know about that are in that region that are just common to us going and looking at all these rock features. And yet they are a huge, um, controversial sort of how did this form in all of geology. And there's no, you know, definite standard for any of these, features, I would say. Maybe the Grand Canyon is the most, accepted, but they're still even fighting about, how did that form. But a big thing is the Colorado Plateau. And I think a big part of it is that uniformitarian geologists don't want to relate all these major features together or put them all in the same time. If you have them all forming at the same time with rapid plate tectonic conditions, um, you can get the Colorado Plateau to uplift and the Rocky Mountains to uplift. But if you're doing it really, really slowly, when I was at NIU, we were spending semesters and seminars reading things, trying to figure out how can you have the Rocky Mountains form, but the Colorado Plateau, which is between the plate boundary and the Rocky Mountains, and it's undeformed. It just uplifted straight up, and it's not compressed. It doesn't have wavy layers in it. How did that get uplifted and not get affected if it's compression from the plate boundary that caused the Rocky Mountains to uplift? Why did it
Mm.
bypass the Colorado Plateau? And, I think a big part of it is not imagining that everything is moving really, really quickly, and then the Rocky Mountains and the Colorado Plateau kinda uplift at the end of this period towards the end of the flood or post-flood. You get the uplift of probably a lot of the world's, mountains because everything has moved around, it's shifted, it causes really strange, mantle dynamics, that cause, sort of this, isostatic rebound to occur is what
Well,
it's called, where you have the uplift of whole regions just straight up because of, sort of the earth settling after this chaotic event. And yeah, that's sort of the nature of it without getting into too much technical detail is sort of, catastrophic plate tectonics can help us explain all these features. If we're saying, let's not put them millions and millions of years apart, let's be like, this kinda happened all together, and that's why everything is so chaotic and ended up being this way. You need a period of time of chaos to explain all of these uplifts and crazy features that you see in Western North America.
yeah. Yeah, I can imagine at the end of the flood, you've had this catastrophic event where continents have moved around, ocean basins have opened up. You're gonna have all kinds of crustal blocks that are out of equilibrium and blocks which are depressed, which are gonna kinda be springing back up and,
Hey,
and vice versa. So, yeah, I can imagine all kinds of readjustments going on, um, which
yeah.
themselves are gonna be quite catastrophic because 'cause they're gonna happen sort of quite quickly after the flood. And so you probably have quite a dynamic early post-flood period too.
You probably do, and I always find it interesting when I read some of, like, in the Psalms and even in Job where it talks about, God who lifts up the mountains and things like that. I don't think we today would use that technology. The mountains are just there, right? But to, just post-flood, you know people that are living, they're literally watching the mountains raise up before their eyes and things like that. I don't know, it just whenever I read passages like that in the Bible, I'm like, that's cool. I can imagine, it was humans watching this happen post-flood, and I think it's also why, this is just my opinion, but conjecture about the native people who would worship the mountains and everything because they're still, moving and active, they probably seem alive, and they're like, "They must be gods, let's worship them."
Yeah. Yeah, yeah. Todd, have you got any questions before I move on? I've got another question I wanna ask.
Oh, I'm still trying to digest the speed of
Digest
movement.
it.
It's crazy. I mean,
Yeah.
but it makes sense, right? It makes sense what you're saying with all these peculiar features. And I've noticed that myself just in my own reading where this looks like it's a ripple mark from this collision. Well, no, it can't be because they're 30 million years apart. And I think, okay, well, I guess they must be different. But no, not if
Mm-mm.
30 million years is like a week. They could be very easily
Yeah.
directly correlated as causal things. And I've seen that in a lot of different things that I've read about. And it's always struck me as odd that what seems to be the most obvious explanation for some of these geological features ends up being impossible because they're millions of years apart. Well, maybe they're not.
Yeah. Yeah.
Mhm.
Yeah. One of the things that has always impressed me about catastrophic plate tectonics is its sort of explanatory power, and predictive power, because there are some predictions that kinda came out of, uh, John Baumgardner's work, for example, that we didn't have at the time the ability to test those ideas, but subsequently we've been able to confirm the predictions of the model. So I'm thinking, for example, of in catastrophic plate tectonics, the modeling suggested that those descending plates that are sinking through the mantle, they go right the way down through the mantle. They go
Mhm.
right to the top of the core.
Mhm.
That wasn't expected in conventional plate tectonics because
Mhm.
there's a kind of phase change in the upper mantle at about 670 kilometers, where there's a change in density,
Yep.
and people thought that the plates were going to get stuck. You know, there was going to be a kind of plate graveyard in the upper part of the mantle where these plates sort of couldn't penetrate that barrier. But at the time, we didn't have a way of kind of testing those ideas. But development of seismic techniques, seismic tomography, through the late 80s and through the 90s has kind of shown that, sure enough, you know, there are these cold slabs of rock below subduction zones. They go right the way down to the top of the core.
No, and it makes
Um,
no sense in conventional geology. How did
no.
they get down there? How can it pass that 660 barrier?
Mhm.
It'd be impenetrable if we're talking centimeters per year rate.
Yeah.
Uh, this is something that was kind of discovered, the deep mantle mineral stress changes that occur once you start getting the rates that you do, with Dr. Baumgardner and also Dr. Cho, Hishin Cho at Liberty has done some significant work on this, doing some modeling to show that you actually have a weakening of the mantle when you speed up the subduction of the plate. And so if it's going fast, it can get past that 660.
Wow.
Yeah. Yeah.
And shouldn't
This is
just
go
clarify
ahead.
this for me. If a big slab of crust has been down that deep in the mantle for 100 million years, shouldn't it have equilibrated in temperature by now? I mean, I don't
Yes.
really know how well rock conducts heat and that sort of thing, but it seems like 100 million years should be more than enough time for the cold signature to go away and you wouldn't be able to see it anymore. Or am I wrong? I don't know. I'm not a
You're exactly right, and that's another thing that they can't explain. Why are we still even able to image these? Shouldn't they have already assimilated into the mantle by now? If the size of these slabs going all the way down to the core, that you're talking about millions and millions of years worth of subducted plate material, which means the stuff at the bottom, if it's going slow, has been down there, what, 100 million
Yeah,
years?
yeah.
Yeah.
Why can we even image it? It should have melted and mixed in with everything else and not even be visible, but that's not the
Yeah.
case.
Yeah. And this is one of the things that I found very impressive about CPT, that this ability to sort of predict observations that are then sort of confirmed later. And that's one of the hallmarks of a good scientific theory, right? That
Yep.
you can explain a broad range of data and you can make some successful predictions, and that gives you some confidence that you're sort of on the right track. Um, but that kind of leads me then to the other question I wanted to ask, which is, um, although it's a very successful theory, obviously there's a lot more still to do. There's a lot more research to be done to develop the model, um, to apply it in lots of other situations. What kind of what are the unanswered questions? What are the big sort of problems that still are outstanding? And how would creationists, I mean, if there are young creationists who are watching this, who maybe are interested in studying geology, geophysics, um, what are some of the questions they might think about sort of contributing to in the future if they became scientists?
Oh, there's so much work to do still with catastrophic plate tectonics. We just need people who are willing to do it. I mean, just fleshing out the story in each region of how specifically these things happened. I mean, Western North America was like it's the low hanging fruit, and we haven't totally resolved it. I already feel like the theory has helped explain things better than uniformitarian geologists, but it's just endless. I mean, what about South America? I mean, it has a similar sort of feature on the western coast. How do we correlate that? What is the exact timing of these features as they formed, and what does it tell us about the flood? and Europe, India. There's just so many things that we could students could be interested in and, and study. It's literally endless, and this is just the geophysics side of thing that I'm telling you. I mean, it's just endless if you're, you know, a sedimentologist going out and actually looking at the rocks and looking for evidence of features in the sedimentology that show catastrophic plate tectonics. Metamorphic petrology, which I was talking about. How do we explain these mineral assemblages that uniformitarian geologists can't explain? Are you good with a microscope? Yeah, make some thin sections and start looking at this, and let's figure out, what conditions are necessary for this to happen. And yeah, there's just man, there's so much work to be done. And if anyone watches this and wants to get in contact with me, I'll put them in contact with people at Liberty and other things depending on their interest to get 'em.
Yeah. Yeah. No, that's great. There's so much to do, and we've said this before, but if you're a student and you're interested in getting involved in creation research, you can almost pick your discipline. You can pick
Yeah.
your field. There's so much that you can do. Whatever you're interested in, there will be something for you to
That's
do in
right.
that area.
Yeah, that's
Um,
true. We need more people to work
we
on it.
do. We do. Yeah. So you geophysicists and geologists, yeah, get in touch with Sarah, get in touch with us, and we'll point you in the right direction. That's brilliant. Thank you so much for your time. I'm sure we will come back to catastrophic plate tectonics again because it's such a fascinating subject, and I'm sure we will cover it in future episodes and look at other aspects of this. Um, but thank you so much, Sarah, for sort of talking us through all of that. And yeah, what are your plans for the future? You're continuing to teach at Liberty, is that right?
My focus right now has been on sort of the education teaching at Liberty. It's a great university for learning about creation science, and I do the online stuff, but then I'm also involved with on-campus faculty as well. There's ongoing research slash education meetings that we have every 2 weeks with people there that are open to a lot of different, creation science people, and we learn about creation science together and talk about strategies for research and education on it. So that's been my sort of ongoing focus with regards to creation stuff.
Yeah, great, great. Okay, well, I think we'll call it a day there. Thank you so much once again. That was really interesting conversation. Um, as ever, we don't know what's coming next, Todd. In our next
No, we
episode,
never do.
we do wing this. We don't know what's going to be scheduled next, but I'm sure it'll be fun. So do make sure that you join us in another 2 weeks' time, and we'll see you all then. Bye
See
for
you.
now.
See you then.
Thanks for listening to this episode of Let's Talk Creation. For more information, visit us at letstalkcreation.org, where you'll find an archive of past episodes and all our show notes. If you'd like to leave a comment or make a suggestion, you can find us on all the major social media platforms. Let's Talk Creation is brought to you in the U.S. by Core Academy of Science and in the U.K. by Biblical Creation Trust. As a listener-supported ministry, we are grateful for all of your financial support. Find out how you can make a contribution at our website, letstalkcreation.org. Also remember to like, subscribe, and share this episode with your friends. Thanks, and see you next time.